My name's Charlie Hirst. I'm a second year PhD student in the Nuclear Science and Engineering department, working with Professor Mike Short in his mesoscale nuclear materials lab. And so we are investigating nuclear materials and what radiation does to materials when it passes through it. I'm from England, a small village in the north of England, and I went to university, to the University of Oxford, to study material science. So I was always really interested in materials because everything in the world is made out of materials. And so that subject involves explaining how the structure of inside materials controls how they behave on a macro scale. The concept behind our project is that when radiation goes into materials and causes damage, it leaves behind some of its energy that it carries with it, and so it changes the internal makings of the material and leaves behind defects which have an associated stored energy. And so what we're trying to do is to use this energy stored in the material as a measure for how much damage is in the material. And this damage determines the properties of the material. So if we can measure how much energy is stored and in what form this energy is stored, then we can determine how the material will behave on the macro scale. We're using a device called a calorimeter, and so we are taking our irradiated samples and heating them up until these defects move around and go to sinks and disappear, and they release their energy in the form of heat. So we measure the heat released from the sample as we are raising the temperature and measure that, and we can, from the graph of energy spectrum, we can determine at what temperature the defects start to move and what energy they release to determine how big they were. And from that we can build a full picture of what's inside the material. Currently in nuclear materials, there isn't really a well accepted unit to quantify damage in materials. It's described currently by the number of times each atom has been moved around in the material. But as you can imagine, an atom could move two places. It could move one hop to the left and one hop to the right, and it would finish up in the position it originally started in. So what we're trying to do is to measure atoms that have been moved and have stayed displaced in the material. So we take into account this recombination, and so we're not going to overestimate the damage in the material. It's pretty exciting because this has never been done before. It's really got a sound basis in theory, and so what we're trying to do is bring it into practice and see if this can be used in industry and in research. It's really going to hopefully change the field. It's going to accelerate the innovation in nuclear materials, because at the moment it takes many, many years to discover what's happening inside the material. But the beauty of our setup is that we're going to be able to hopefully irradiate materials and test them within seconds.